Sent out an email to a handful of you, maybe like an hour ago. You didn't get an email from me, don't worry about it. The people who did, I'm worried about some of you who are not doing very well on your lab assignments and or your homework and or your quizzes. And the combination of all of them has you failing the class already. Now, you already know who you are. But if you're in that boat, some of you I didn't send an email to because we've already had a conversation. But if you're in that boat, something needs to change, right? If you can't do it on a quiz where you use your notes, or a homework where you can come to my office hour or go to the math lab for help, how are you going to do it on a test, right? I mean, so I want to be able to help you figure out what you need to do. A lot of it is, and you guys are all learning this, we've been having this conversation too, amount of quality time you spend with calculus. And everybody's amount of quality time is different. That's necessary to really master it. What'd you say?
I'm saying I'm spending like 8 hours a lab.
Okay, so he says he's spending 8 hours a lab. So then the question becomes, is that quality time or is that just time? And that's what I'm questioning you. But that's kind of the question you need to be asking yourself. I'm spending this time, but can I do it better? Can I be more efficient? Or why is this not working for me? Or do I just need 8 hours to do the lab? That's the other thing that we all learn in calculus. There's going to be the guy next to you who does the whole assignment in 20 minutes while he's watching TV and eating dinner. And then there's you who spends a day and a half working on it because it's more of a challenge for you. And we all just have different strengths and weaknesses. I compare it to if we all went right now to a basketball court and started shooting free throws. Some of you would do a lot better than me. And if I wanted to keep up with some of you, I would have to practice for days because I can't play basketball. So, I mean, there's just some of us are quicker, some of us aren't. And if I wanted to keep up, I just know that I'd have to spend more time. So it's kind of the same thing. It's not as fun as basketball, unless you're a total nerd like me, and you might think it is. It's way more fun than basketball. All depends. Okay, let's move on then. Section 7.2, trig integrals. Yay, this is page, what page am I on, 33? Before we start with this, I want to add to my little list over here of trig facts. I've crammed them way over here in the corner. Can you see them? Okay, I've crammed them way over here in the corner. These are things that we need to know. Hopefully most of us know some of them. Ideally, all of us will know all of them very soon. So the first one, what's the derivative of sine x? Cosine x. We need to know that. And the derivative of cosine? Negative sine. What about tangent?
Secant squared.
Secant squared. Some are going, oh yeah, I think I remember that. What about secant?
Secant x tan x?
Yeah, secant x times tan x. Did you review those or you just know them, Zach? What is it? You'll never tell, right?
I think you already know.
So these are these four. There's also cosecant and cotangent. Those are going to come up less often, so I'm not going to list them right now. You'll even see it in our examples in this section. I kind of just skip over a lot of them, the problems that have cosecant and cotangent. They behave very similar to these, so it's kind of just redundant to do them again. But most of what I will expect of you is that you will know these four for sure. My other question for you is, what are some trig identities that you remember? I want a couple of those up here. Anybody remember some trig identities? There's a lot of them. Take hands. Anybody? Yeah, what do you got?
Sine squared x plus cosine squared x equals 1.
Ooh, that's a big one. We're going to use that one pretty much almost every other day for the rest of the semester. That's called the Pythagorean identity. You guys remember that one? That one's going to come up for sure. We'll probably even use that today. Actually, I will, maybe in my first example. How many other trig identities that you know?
Sine over cosine equals tangent.
Ooh, I like that one too. Tangent is sine over cosine.
And if flip it, it will be cotangent.
Beautiful. And if we flip it, it'd be cotangent. I'm not going to write that one down, but that one too. Cosine over sine would be cotangent. What are some other ones that you've seen that you think you might remember?
1 over secant x is...
I don't know if I can squeeze those all on here, but you're right. So the relationship between sine and cosecant, the reciprocals, cosine and secant, and cotangent and tangent are the ones that are all reciprocals of each other. What's the reciprocal one? Yeah, what do you got, Chad?
1 plus tangent squared is equal to secant squared.
That's another one we're going to use a lot of. This is not one, by the way, that I have memorized. but I claim that it's already up here in disguise. I will give you this on an exam, by the way. I'll remind you of this and this. I won't tell you that one you should know. This one's actually already up here in disguise. I'll grab this red pen to show you. Imagine if I divide everything here by cosine squared. I'm going to do it really loosely because I'm going to erase it here in a minute. I divide everything here by cosine squared. If I did that, what's sine squared over cosine squared? Tangent squared, right? Cosine squared over cosine squared? 1. And 1 over cosine, we just talked about, that's secant. So secant squared. So I only have this first one memorized, and I can get the other one by just doing a little algebra trick like that.
You could also divide it all by cosine and then.
Yes, and then you get the other one, the one that we're going to use less often. If we divide everything by sine, we will get that 1 plus cotangent squared equals cosecant squared. So we're going to leave these ones up here for now. There's some other ones that we're going to need in a little bit. But these are some that we're going to use all the time, and if you don't have them down, practice writing them down every day, make some flashcards and challenge yourself, whatever, just to keep them fresh, because they're going to keep coming up. All right, so let's talk about 7.2. It's all about trig integrals, and the very first example isn't even labeled an example, it's just that it's review. How do we evaluate the following? It's review. So if we haven't learned anything about trig integrals, and it's supposed to be review, maybe it's integration by parts. Why do you say that? Because it looks like it. Okay, so you're right though. What about it looks like integration by parts? Yeah, you've got multiplication going on there, so that makes it look like integration by parts. So integration by parts would be a good idea to start with. But remember what I said last time about integration by parts. We don't ever want to do integration by parts unless we checked what first? U sub. And U sub usually is when you see a function inside another function. This is not so obvious, but it really is, because this really is this function like this, right? Sine to the fifth is really sine x to the fifth. So sine really is an inside function. And if we let u be sine x, what's du? Cosine x dx. So this part right here is just going to be u to the fifth. And cosine x dx is just du. So we can rewrite this as u to the fifth du. So you're not totally wrong to think integration by parts. We just learned it, we see multiplication, but always look to see if maybe u sub will work. It's a lot easier. Integration by parts would have gotten you there, so it would have taken you a while. Everyone okay where I got to, how I got to there? What's the integral of that? U to the 6 over 6 plus d.
Yeah.
And then we put the u's back in there to go back to our x's. I like to put the constants in front, it doesn't really matter. That's sine to the 6x plus c. Putting the sine x back in there. So it actually was a u substitution problem. How could we tell that it was the u substitution problem just by looking at it? How do we know it was going to work?
The integral of sine
The integral of sine?
was kind of cosine.
Oh, the derivative. So the
Derivative,
derivative of sine is cosine, and it's hanging around in that problem. There's the derivative. If I let u be this, I see the derivative of that hanging around. That's what tells you that that u sub would be the. If this had been a cosine squared, I wouldn't have been so happy, because that's not the derivative of sine, and I've got extra stuff hanging around there. So if you look at what I said on the notes here, it says, I want to see what the words are. Oh, it's down maybe 2/3 of the way down where it says integrating sine and cosine. It says where substitution is not an immediate option. It was an immediate option in this case because the derivative was hanging around. Is everyone okay with what I mean by the derivative hanging around? If you're not sure, you'll ask me now. Okay. So what then if we do this next one, where it's not an immediate option? What if it's just sine to the 5th x? I don't have an extra cosine hanging around that makes it an immediate option. Right, that one over there was so nice because that cosine was there. I can't hear you, Joseph.
I'm thinking.
Thinking out loud, that's good. That's good for you. We could try integration by parts, like we could break it up and do parts. We actually can do u sub with this, it's just not obvious yet. So that's the whole point of this section, is to figure out how to attack things like this. So the first step is, right underneath that I said, it's not set up for substitution, but it would be nice if we just had one sine x or one cosine x, like we had here, right? Just one of those cosines, that'd be nice. So what we're going to do is we're going to rewrite it. We're going to rewrite this as sine to the 4th x times sine x dx. I haven't changed the problem, I just changed the way it looked. Now this part right here is going to be my friend. Which trig function do I take the derivative of to get a sine? Doesn't have to be positive or negative, I just want to know if it's a cosine or a sine or a tangent or whatever. Cosine, right? Cosine we just talked about gives us a negative sign. So I'm actually going to choose u equal cosine x. And you guys are all going, Jill, there isn't even a single cosine in that problem. Why are you choosing that to be u if there's no cosine in that problem? Ah, the identity's putting some cosines in there. Let's go back to our favorite one over here. This guy right here is our favorite identity right now. I have some sines in there, some sine squareds or sine to the 4th. That's related to cosine squared somehow. So it is actually in that problem, we just don't see it yet. So let's keep going. If I choose that for u, what's du?
Negative sine.
Negative sine x dx. So this sine x dx that I have up here, yeah, I'm going to have to solve for that. Sine x dx is equal to the negative of du. Agree with that? I'm just kind of looking at this extra piece over here. So I'm going to put that in there. I have sine to the 4th x. All of that is negative du. I'm going to put the du here and the negative all the way out in front. Don't lose that negative sign in front. It's okay with that negative? Remove my equals because it's in the way. So far so good, except that everything's supposed to now be in terms of u. I can't leave sine to the 4th x in there. It's supposed to be in terms of u, where u is equal to cosine x. So I have to figure out how sine to the 4th is related to cosine x. I'm going to do it off here to the side a little bit. Sine to the 4th x is equal to sine squared x squared. Agreed? Come back over here to my favorite identity of the day. If you solve this for sine squared, what do you get? Sine squared equals 1 minus cosine squared. So this equals 1 minus cosine squared squared. Well, messy trig identities, we love them. Why did I do this again?
In order to plug in the cosine.
Yeah, because my u was cosine. If my u is cosine, I need to make everything in terms of cosine. You can copy it down and follow it, but if you don't know the y, you're in trouble, right? You don't know why we're doing it. So the goal is to turn everything into cosines. So I took my sine to the 4th and now I've changed it into cosines. So now I'm going to keep going. Cosine is u. So this is u squared? Squared? I'm just reworking that sine to the fourth portion of it, just to make sure we see where that came from. So now, I have this mess. Negative the integral of 1 minus u squared squared du. I replaced my sine to the fourth there with what we just found. Everything's in terms of u now. Before I go on, questions? On why or how? Or what? We're good? So how do I integrate this? I should be able to integrate it. Is that you, Alex, said something?
I'm just kidding.
I didn't hear what you said.
You just factor it. That's
Yeah,
fine.
just go ahead and multiply it out. I mean, if you have to simplify using your algebra, simplify using your algebra. So I'm going to multiply that out into 1 minus 2u squared plus u to the fourth du. That's the shorthand of multiplying this out using FOIL. 1 minus u squared times 1 minus u squared. If you do enough of them, you start recognizing the pattern. Now we're ready to integrate. Yeah? So I have negative u minus 2/3 u cubed plus 1/5 u to the fifth plus c. I almost hear a pin drop in here. Now what?
Load the values back into.
Yeah, put the u's back in there, so all of my u's need to be changed back into cosines. And I also need to distribute this negative back in there. You guys all right if I do them at the same time?
Yeah.
We can handle that? So that will be negative cosine x plus 2/3 cosine cubed x minus 1/5 cosine to the fifth x plus c. That was a mess. But doable. This is the way your new outlook on calculus needs to be. It's just gonna be messy. But it's doable. As long as you understand the process and you can handle the mess, you'll get there. It's the short and sweet, it's long gone. That was a couple semesters ago at least. Questions? Yes?
I understand how you do it, but I just don't, I'm not seeing why. Like if I looked at the question, I would never think to do u equals cosine x.
Exactly. I'm glad you said that. So everyone hear what Sebastian said? He's like, okay, I follow it, makes sense, but I wouldn't know to start there. And so that's the whole idea, is we need to figure out how to start. So what we did first is I rewrote it by pulling one of these off. This is the part that told me to let u equal cosine, because by pulling the one of them off and having this extra just sine by itself, I know that sine is the derivative of cosine, which is what tells me to let u be that. So u is always going to be the opposite of this one thing you have out here. So even if, like over here, if I hadn't seen what was underneath here, if I couldn't see it, the fact that I just have one cosine right there, I'm going to let u be sine, because that's going to get rid of that cosine by itself. So that's the trick for this one case. There's special cases, and what makes this one special is because this was odd. Because this was an odd exponent, when I pulled one off, I was left with an even number here. It had to be even, otherwise I wouldn't have been able to do this. Like if it was cubed, right? If it was like sine cubed, I can't make that sine squared to the 3/2, 2/3, all of a sudden it's a mess. So because it was odd to begin with, we could break it up into an even and just one extra odd one. And that is what tells me. So the fact that I could pull off the extra, and then my u is always going to be the opposite one. Does that help? So that's actually what it says down there about case 1. So right there, integrating sine and cosine, where substitution is not an immediate option. Case 1 says, let me write the notation out here. The notation looks scarier than it is. It says if you have sine to the n, oops, n comes first. x cosine to the n, m or n is odd. It could both be odd, right? So one of your exponents is odd. If you have sines and cosines and one of your exponents is odd, then you can do this trick that we just did where I call it peel one off, pull the extra one off. So we had sine to the fifth and cosine to the 0 in this problem, right? So we had one of them odd. If you have one of them odd, you can use either one as your odd one. Over here, we had both of them odd. Okay? So as long as one of them's odd, that's the one you're going to pull off. I'm about to show you what to do when it's not as obvious as the last two. When they're both even, we have to do a different trick. So there's little tricks. When they're odd, this is our trick. Pull the extra one off. Other questions or comments? That was really good. I need to know what you're thinking. Like, as you're sitting there going, if I'm doing this on my own, how am I going to know where to start? How am I going to know what to do? Okay, so let's look at example 1 down on the bottom. Oh, by the way, it says right underneath there, just peel one of them off. Whichever one is odd, peel that one off. And then use that identity every time. If they're both odd, you'll get the same answer either way. So example 1 has the integral of sine to the 6th x cosine cubed x dx. So one of them's odd, that's good. But only one of them's odd. The cosine is odd. So I pull off the extra from the odd one. So I'm going to rewrite this as, I'm going to leave this alone, cosine squared times an extra cosine. Everyone okay what I mean there? So I'm going to rewrite this as sine to the 6th, cosine squared, and here's an extra cosine. So this technique will work because when you peel one off, everything else is even, right? Here's the one odd guy. Everything else here is even. That tells me we're on the right track. If this is cosine, which one do I want to be u? Sine. It's always the opposite. So we're going to let u be sine x. Du is cosine x dx. So here's my du. This guy right here is du. What's this?
U to the 6th.
U to the 6th. What should I do with that?
You're gonna work it out to the side.
Ah, she's pointing over here at the identity again. Work it out using this identity. Cosine squared equals 1 minus sine squared. I'll put it right underneath here, kind of in small little. Is that your hand up, Brielle?
Yeah.
What's up?
For the u, why isn't it negative sign?
You could use a negative sign if you wanted to, but you just use either a cosine or sine, whichever one's going to give you the correct function when you take the derivative. So if you choose negative, it'll still work out. It's just easier to start with a positive one, because the negatives work out in the problem anyhow. It doesn't matter. I could use sine or a negative sign. So we're thinking of this as 1 minus sine squared. So what is it in terms of u? 1 minus u squared. So I think we're good. We have u to the 6th times 1 minus u squared times du. Sebastian, make sense that time in terms of which way to start? Okay, good. Now what?
Integrate.
No, I can't integrate yet.
Oh,
Simplify first, multiply, multiply this out. U to the 6th minus u to the 8th du. We can integrate that. 1/7 u to the 7th minus 1/9 u to the 9th plus c. Are we done?
Plug your brand.
Yeah, put the x's back in there, the original problem had x's, there's no u's in that original problem. So the answer is 1/7 sine to the 7th x minus 1/9 sine to the 9th x. Let's see. Questions? So let's say this problem is on the exam, and I finish the exam with half an hour to spare, and I want to check my work. How can I check my work?
Is it with the power rule?
What do you mean? I think I'm following you, but give me a little more information.
Isn't this just the power rule in reverse?
Right, so are you talking about taking the derivative?
Yeah.
Yeah, so that's the part you were missing. So if we take the derivative of this using the power rule, what should the answer be? He's pointing up here. It better be this, right? If I've integrated correctly, when I take the derivative of that, it should equal this guy. Should. I just want to check it real quick because I'm feeling a little nervous when I look at it. Maybe I made a mistake and none of you caught it. Or maybe you're too shy, you don't want to point out that I was wrong. So if I take the derivative of this, I have 1/7 times 7 sine to the 6th x, right? We're bringing down the 7, subtracting 1, times, what else? What else did we multiply here? Cosine x, chain rule, right? We bring down the 7 and then multiply by the derivative of the inside. It's the chain rule. Remember, this is sine x to the 7th, right? So we bring down the 7, make it a 6, times the derivative of the inside. Minus 1/9 times 9 sine to the 8th x times cosine x, same reasoning, plus 0. This does not look like the original problem. Doesn't look like the original problem. Something must be wrong. Or maybe it's not wrong.
What if we're not accounting for the C?
Well, we are accounting for the c because the derivative of a constant is 0. So there's a plus 0 right there. That's not enough to do it. I claim that this expression right here is equal to this expression right here. It just doesn't look like it right now. Remember my best friend over here in the corner? I bet if we use this best friend of mine over here in the corner, we could make that look like the original problem. So let's do a little investigation. This problem has sine to the 6th and cosine cubed. Here's a sine to the 6th and a cosine. I'm feeling pretty good about that. This one has a sine to the 8th in it. That's like a few too many sines compared to the original problem. Maybe I could change one of the sine squareds back into cosines. I'm not going to do the whole problem because we're going to run out of time, but I'm just going to show you what we could do. I might keep this guy and run that around. Minus, I'm going to make this sine squared times sine to the 6th. So here's my sine to the 6th. But my sine squared is going to be a 1 minus cosine squared. And then there's another cosine. So what I did is I took this 8 and made it a 6 and a 2. Distribute that, combine like terms, it's exactly this. So when you go to check your work, what's tricky with trig is you may not look at something that looks like the right answer, especially when I give you the lab answers for chapter 7 a little bit. You may have a correct answer that doesn't look like mine because of an identity. Doesn't mean you're wrong, it just doesn't look like mine, it's written a different way. to show that it will work. Don't trust me. Just a little warning, don't assume you're wrong because it doesn't match. Yes?
On test, do you want us to use the identity to rearrange the factors?
No, I don't. But I just, in general, if you're checking your work, that's, my warning is that you take the derivative and you'll be going, wait, that's not right. Maybe it is. On a test, I'm not gonna require you to check your work like that, especially if this one, we're not even done yet. It takes a while. But just a warning that when you check these, it doesn't always look correct, but it is. I mean, something like some of you already know that this is the same as this, right? The same answer, one's rationalized, one's not. I'll take either one, right? So again, they don't look identical, but they are identical. Same kind of idea. The trig is even harder to recognize though because of all those identities. How are we doing? Okay, so those odd ones are the easy ones. If you've got one of them odd that you can peel one off, it's a nice U sub problem, maybe some algebra. Those are the easy ones. The ones that are even are a little bit messier. A little bit messier. I'm gonna go. I don't know if they're harder, but they're definitely messier. So if you flip over the next page, case 2 is, what if both of your exponents are even? So case 1 is they're both odd, or excuse me, one of them is odd. Case 2 is that they're both even. To do that, we need 2 more, actually 3 more identities, depending on what type of problem we have. A couple more identities. Let's see if I can squeeze them over here in my corner. I have them written there on your paper. We call them the reduction formulas. There's formulas that reduce cosine squared and sine squared down to get rid of the exponents. What did I say? Again, this formula will be given to you on the exam. You don't have to have it memorized. A lot of you will have it memorized soon because it comes up that often. And then there's this formula. Very similar, actually. They both have a cosine in them, it's correct. And then the last one that's down there is sine 2x. I just helped somebody in another class earlier who had the same problem. Is equal to 2 sine x cosine x. These are interchangeable. All of these will be given to you on an exam. You'll see where we need them in a few minutes. This one and a couple more, maybe after the break. So those are all there. So what we do when we have all even powers is we use those 2 identities to break down our integrals so that the exponents get smaller. So that they're smaller, we can integrate them. Just sine to the 1, I can handle it. Sine 8, but I don't know how to integrate sine to the 8. So let's jump in with example 2, which by the way, if you're looking at your notes, example 2 starts way up here near the top of the page. And then I have a couple of blank lines for you, which we're going to fill in. Then there's a bunch of simplifying in the middle that I've already typed for you. And then there's a lot more we have to fill in, and all the way at the bottom we finally get to the answer. And we'll be lucky if we all can fit it on one page. I write fairly small, some of you don't. So if you don't think you write small enough, you might want to pull out a separate paper or something. Okay, so we're going to get through example 2. We got this. We'll start over here. Example 2. I have a special shirt that I wear when things get really hard. And I considered wearing it today, but I think I'm going to save it for Tuesday. Just so you know. On Tuesday I'll wear my special shirt. So this isn't the really hard bit. I think Tuesday's a little bit harder. Okay, so the integral of sine to the 4th x cosine squared x dx. Why does the trick that we were doing here not work in this case?
They're both even,
Yeah, they're both even, which is part of it. And if I pull one off, like if let's say I pull off one of those cosines, so sine would be my u then, and I'd have an extra cosine hanging around, just cosine to the 1, right? If I pulled one of them off, I'd have an extra 1, and identity only works with even powers. See what I'm saying? We can't break this up into cosine times cosine. because I need a square to use this identity. So that's why we can't pull off an extra one. So when we have even powers, all we use are these two reduction formulas. Break down these cosines and sine squareds into these double angles. So, I'm going to rewrite this one as sine squared squared again. And this is already a cosine squared. Always looking for sine squareds and cosine squareds, because those are our identities. That's the first step. So on the next line down, I'm going to put these formulas in there. So that's equal to the integral. Instead of sine squared, I'm going to write what it's equal to here. I'm putting it in brackets so I don't lose everything. Here's sine squared, and then it's squared. Sine squared. Squared, that's just this part. I'll use some colors so you can follow. If this is the green dot here, that's the green dot there. I've only done the first part of it. Just plug it in that identity. What'd you say? Thinking out loud again? Okay. And now for cosine squared, I'm going to put this guy in there. 1/2 times 1 plus cosine 2x. Dx. Okay, Jill, you say it's going to get better. I don't see it yet. Okay. So the next line down I have there for you. Let's see if we can figure out where it comes from. I'm going to write it on the board here, and then we're going to do some simplifying in a minute. The next one is written like this. I want to talk about where this comes from. 2x. If I just don't copy it, I just simplify on my own. It looks like this. Where did all that come from? Any piece of it?
It's 1/2 cubed.
Okay, I like it. He says 1/8 is 1/2 cubed. Because this 1/2 is squared times another 1/2. That's where the 1/8 came from? Okay. I got that. So all the 1/2s came out front and became a 1/8. See where this came from? Yeah, it's right there. We just brought it down. So the only other thing is, where did this come from? Yeah, multiplying out the 1 minus cosine 2x squared. Using FOIL or the shorthand way to multiply out. 1 minus cosine 2x times 1 minus cosine 2x. You guys all right there? So then the next 3 lines are just actually multiplying this all out. So there's 6 different multiplication problems in here. Multiplying 1 times that and 2 times all that stuff going on. So I left all that busy work for you just to copy. It's there for it to copy down. So it does all that, and then it combines like terms. So there's a couple missing algebra steps in here. And so the next one that I have printed for you looks like this. I'm at the bottom of the part that's printed. I have to move over to the next page, the next board here in a second. So if you were to multiply that all out, combine like terms, that's what you would end up with. That's just some busy algebra work. You okay with that? Alrighty then. So notice the next line I have there. I have a 1/8 and a whole bunch of integrals set up for you, blank ones. What we're going to do is integrate each term separately, because we need a different technique for every term. So on that next line down, we're going to start filling in. We should have 4 integrals. The 1/8 is still out front. So I have 1/8. And then the first integral is just the 1. Just integrating the first term is a 1. And then minus, the next integral is cosine 2x. Breaking up each term separately. The next one is negative cosine squared. And positive, yeah. Integral of cosine cubed 2x. Oops, I lost my dx right here. Use that back in there. So I have 4 different integrals. Oops, and then I have to close my brackets. You guys all see where those all 4 came from? Each term separately? I would like to believe that you can integrate this easily. I'm going to go with that. I would like to believe that you can integrate this fairly easily. Fairly, I put the word fairly in there. Because when you integrate it, you'll get a sign, and what do you have to do with that? 2x in there. Yeah, you're going to have a 1/2 out front because of the chain rule, right? So these 2 are fairly easy. What about that guy? I don't think U sub's gonna work because it's even. Yeah, Jose?
You use the trig property again? and then-
Yeah, gotta use the trig property again. Now you know why I wanted to wear my shirt. I'm not even wearing it. Wait till next time. So because this is an even power of cosine, I've got to use that reduction power again. So I'm going to put a little note there. Need formula again. Because that's even, right? And what about that last one?
Formula again?
It's not the formula again because it's odd. Right? That's an odd. So I need to pull off one of the cosines, Nick is saying. He's smiling. It's not a grimace. I think he's actually enjoying himself. I'm just saying. Don't tell me the truth. Let me believe that you're having fun. He's loving it. See, did you guys hear that? He said he's loving it. Like McDonald's.
It was sarcasm.
What'd you say?
It was sarcasm.
I don't speak sarcasm. I'm sure he meant it. Everyone see it's odd, so I need to pull off one of the cosines? It's odd, so I need to pull off one cosine, which is what we're going to do on the next line down. Now you know why it takes a whole page. Okay, so here we go. We can do the next line, a little bit at a time. I'm going to work out some of the integrals and not others because some need some more work. Can we integrate this one?
Yeah.
Okay, good. What's the integral?
X.
X. Fabulous. That's how easy this is. X. Minus, what's the integral of cosine 2x? 1/2 sine 2x. We can integrate those two, no problem. This one I'm going to rewrite with the formula though. So I'm going to keep it as an integral because I'm not ready to integrate it yet. I need the formula still there. What is the formula going to give me? Formula's over there behind me. 1/2 times 1 plus cosine of 2x, but because I already have a 2x in there, it has to be doubled. It's going to be a 4x. This formula says whatever's in your cosine, it's doubled. So because I have a 2x right here, there's a 2x in there, I have to double that. This becomes cosine of 4x. Oh, that's fun. Change the definition of fun, remember? Plus, I'm not going to do it yet, I'm just rewriting things. I'm going to rewrite that one as cosine squared times cosine. Keeping my 2x's because they're all 2x's in there. Cosine squared 2x times another cosine 2x dx. Lots going on there. You giving up, Jake? He's like, I'm done. I had enough. We're ready for a break yet? We stop another problem? I don't think so. All right, so what's next? What do you want to do next? We got spaces there, we're supposed to be filling in something. These are done.
We can just focus on those two.
Yeah, let's just focus on these two. I'm just gonna recopy what I have here then, so I don't lose it. So this part's all good. Here I'm gonna bring the 1/2 out front. And then I'm integrating these two terms. The integral of 1 x plus, be careful here, the integral of cosine 4x.
Sine.
4x.
Sine 4x over 4, we're gonna have a 1/4, right? Just like we had a 1/2 earlier. So here's the minus from here, the 1/2, which is the constant, and I integrated each of those two terms. Still good, Nick? I see you pointing. Did I lose you?
Yeah,
Where did I lose you?
on just that piece right
This piece?
there.
So we're integrating the cosine 4x. So the integral of cosine is a sine. So that's where the sine 4x came from. But because the derivative of the inside is 4, we have to divide by that 4. Because when you go to do the chain rule, when you check it later, the derivative is cosine, and you have to multiply by 4, which will get rid of that. I like to call it the reverse chain rule. You know how the chain rule is you take the derivative and multiply by the derivative of the inside? I'm integrating and dividing by the derivative of the inside. You could also do a u sub, it just it's too time consuming to write it all out. With practice you'll start seeing them more often. Okay, so that's good. What should I be doing over here though? Pythagorean identity? Why?
Because we do cancel out the cosine matrix.
Well, when I have the odd ones, what's my goal? What do I do first? A u sub. I have to know what u is. What's u?
Sine.
Sine. Because I have one cosine pulled off, so use the opposite one. So sine 2x is going to be my u. Let's squeeze that over here off in the corner. U is going to be sine 2x. So what's du?
Negative sine. I mean 1/2 negative sine x.
Taking the derivative, careful. You're going the wrong way, I believe. Cosine 2x times 2, because of the chain rule, dx. Chain rule, right? Derivative of sine is cosine, derivative of the inside is 2. So this part right here, cosine 2x dx is what I have inside there. I almost have that. Here it is right there. So what is cosine x 2x equal to? And cosine 2x dx equal to? 1/2 du. Nobody's head's gonna explode. It only feels like it. Only feels like it. Okay, so do we agree that this part is 1/2 du? The underlined part's 1/2 du. You guys all right if I put the 1/2 in the front?
Yeah.
1/2 du. Cosine squared, that's why I have to use the identity. So you guys were telling me to use the identity earlier. I have to be able to put it in terms of sine. So cosine squared is 1 minus sine squared? So what am I going to write over there? 1 minus u squared, right? We could write sine squared, but eventually the whole goal was to put it back in terms of u. If you need to write it in 2 steps, you could. 1 minus sine squared is 1 minus u squared. Okay, we're about halfway down this page. Okay, maybe we're 2/3. Maybe 3/4 of the way down this page. I think we're getting there. Questions on that? Remember our conversation about being organized last time? Pays off here too. Okay, so I only have one more thing to integrate. I'm feeling pretty good. I'm just going to recopy all of this so I don't lose any of it. I think while I'm recopying, I'm going to distribute right here. Distribute this negative 1/2 right here. Since I'm recopying, I might as well. This will be minus 1/8 sine 4x. right, because I'm distributing my negative 1/2 through there. Plus 1/2 times, what's the integral of this? You're close. It's a du, so the integral of 1 is a u. U minus 1/3 u cubed plus c. So you should be down now to the next line that I have printed for you. Hopefully you're down to there. So the next line that I have printed looks like this. I'm going to recopy it so we can point it out. Plus, people with the video don't have it in their notes. But I'm going to recopy that line. So I'm rewriting the second to last line on the page. And then we're going to talk about where it came from. And then we're going to take a break. Hooray. Okay, so my question for you is, how do we get from here to here?
We did x minus 1/2.
Mm-hmm. X minus 1/2 x, those were like terms. That's 1x minus 1/2 x leaves us with just 1/2 x. Those two terms gave me this. This guy just came from here. Brought it down. This guy just came from there. And this, what's this?
You plug your x back.
Yeah, putting our sine 2x's back in for our u's here. I keep losing the end of my parentheses. And so finally, if you combine like terms, you end up with that very last line. Oops, I'm distributing it all the way through, sorry. The very last line, which is 1/16 x minus 1/64 sine 4x minus 148 sine cubed 2x plus c. That's an 8. Where'd that come from? This one I think is okay, right? This 1/2 times 1/8, that's easy. The 1/64 sine 4x came from this 1/8 times this 1/8. What happened to this guy? Where'd he go? Yeah, this one is minus 1/2 sine 2x. This one with the 1/2 here is going to be a plus 1/2 sine 2x. Those guys are gone. And then this last one over here, be careful, this is 1/2 times 1/3, which is 1/6, times this 1/8, 148. That's our answer. In this one problem that started with 2 evens like an hour ago, we ended up having to do a little bit of everything. We had to do straightforward integration. This was a little reverse chain rule or a little mini U sub. We had to use the formula for evens again. We had to use the trick for odds again, all in one problem. This is not uncommon. We need to take a break though and go get lots of sugar and caffeine and fresh air. Maybe we should just go stand out in the rain for a while. Yeah. Get a little drenched and wake ourselves up. Take a good 10-minute break. We'll come back and do a few more. Yes, sir. That's my little comments on lab assignments. Okay, so you should have, oh yes, the correction. I'm so glad you reminded me. I forgot again. There's a typo on the 7.2 lab, number 7. Number 7 on the 7.2 lab. What page is that? 37. Thank you. Number 7, see how it looks identical to number 6?
Yeah.
It's not that easy. You can't just do the same problem twice. There's not supposed to be an exponent on the tangent. It's just tangent to the first. Time, what was it, secant to the fourth? Secant to the fourth theta. It's the exponent there on the tangent, should not be there.
Yeah.
You guys see it?
Something I just crossed over.
Yeah, I just looked like, that's what I did on mine, just scribbled out the exponent, just not there. Thank you for reminding me, Chad. Wanted to tell you guys like 3 times, I kept forgetting. Okay, so let's keep going because we're having so much fun today. We're on page 35. Now we're going to talk about what to do with tangents and secants. So we had case 1 and case 2 with sines and cosines already, the odds and the evens. Those are the easier ones. Like this last one was easy, right? The ones for tangents and secants are similar to those in that they are using what we know about the derivatives of tangents and secants. The sines and cosines were kind of nice because they're each other's derivatives. The tangents and the secants have different derivatives, but we're still following along with those derivatives. So, erase this example that I have here. So I have at the top of page 35, case 1 is if you have an even number of secants. Case 1 is if you have an even number of secants. Case 1 for tangents. An even number of secants. Why do you think they care about even number of those instead of odd? What'd you say, Joseph?
It'll be one of our trig functions.
Yeah, one of our trig derivatives. One of our trig derivatives, the derivative of tangent, is secant squared. So we're looking for secant squared hanging around now, not just a secant by itself, but if you have secant squared, that's the derivative of tangent. So you know how before we were just looking for one sine or one cosine, because that's for these guys. Now we're looking for even numbers of secants, because that's here. So that's case 1. If case 1, if you have an even number of secants, we're going to peel off secant squared, because we know that's the derivative of tangent. So guess what u we're going to use? What are we going to use? U equals tangent, because this is its derivative. It's always choosing a u whose derivative is hanging around. So if we have an even number of secants, we're going to pull off a secant squared and let u equal tangent. So let's try that with the, my second one is odd, it's case 2. No, gotta be careful. Let's not try with example 3. We'll have to do it with example 4, 3b. Let me write the question here for 3a. So this one is not that case, right? I don't have an even number of secants, so I can't pull off a secant squared. So we're stuck on that one. So that's case 1. Case 2, I just have it listed there. Case 2 is if you have an odd number of tangents. Then we peel off a secant and a tangent. Why? Yeah, to make it the derivative of secant. And if we pull off an odd one, then we've got even ones left again. It's all about leaving the even ones afterwards. What's my u going to be? Secant, right? Because that's the derivative of this guy. By the way, I don't have these memorized. I don't know that, like, if sine is odd, I have to choose u equals cosine, and if tangent is odd, I have to choose u equals secant. I personally don't have these rules memorized. People walk up to me in the lab, is this case 1 or case 2? I don't know which one's which. But what I have memorized are those derivatives. I know I'm trying to pull off those derivatives to be my DUs. That's what I really have memorized. And sometimes a little trial and error. Okay, so let's do one of these. So do we agree this is a case 2 case where I have an odd number of tangents?
Yeah.
Let's show you what's going to happen. So if I have an odd number of tangents, I wanna make sure I have one secant and one tangent to be my derivative. So I'm gonna make this go down to 4. I'm gonna make this go down to 8. And then I will have one secant tangent dx here on the end. This one doesn't matter if it's odd or even in this case. See what I did there? This we need to recognize as the derivative of secant. So my whole goal is make these even and have a derivative over here left over that I recognize. Since this is the derivative of secant, that tells me that u equals secant x. And du is secant tangent. So here's my du. What's this part? What can I do with that? What do you think, Jay? Changing your mind? Yeah, Joseph?
We put that as u to the 8.
Yeah, that's just u to the 8th, right? U was secant, that's just u to the 8th. So this part right here is u to the 8th, because that was my u. This is my du, that's why we picked it, right? What do you think I need to do with tangent to the 4th?
Make
If I squeeze myself back in the corner here.
The trig facts.
Is that you, Megan?
Yeah.
What'd you say?
Use that trig fact, so make the 10 4x, make it 10 squared x to the second, and then change it into secant minus 1.
So she says take the tangent to the 4th, and make it tan squared squared. And the tan squared we can solve for right here in this identity. Let's do that. Let's do that all at once. We'll actually do it in 2 steps so you see it. Tangent to the 4th is tan squared squared. I'm just going to write this part as u to the 8th and du because we already did that part. That's my tangent to the 4th. But tangent squared using this identity is equal to secant squared minus 1. So this is secant squared x minus 1 squared, u to the 8th du. How does that help me?
Because you can change in terms of u.
Because now I can put that in terms of u. U was secant x. So this is u squared minus 1 squared times u to the 8th du. Always feels good when the u's are all that's left. And we got somewhere, now it's all
Just
u's.
distribute.
And what'd you say, distribute?
Now we do this factor.
Yeah, we've got to multiply this out first. Distribute that u to the 8th, do some algebra here. We love algebra. It's our friend. So when we multiply that out, we get u to the 4th minus 2u squared plus 1. Then we have to still multiply it by u to the 8th. Again, just multiplying that out. So we end up with u to the 12th minus 2u to the 10th plus u to the 8th du. Ready to integrate? No problem. 1/13 u to the 13th minus 2/11 u to the 11th plus 1/9 u to the 9th plus c. Still good? All done? Am I done? The box around it? Little heart? Valentine's Day? No? Yes?
Plug your sticker.
Gotta put my secant x back in there. Make sure you keep going back to the original variable. That u was just a little thing to keep our place for a while. We have to go back to the original variable. So the answer is 1/13 secant to the 13th x minus 2/11 secant to the 11th x plus 1/9 secant to the 9th x plus secant. They're messy, but they're doable. You need to know your derivatives, and you need to know your identities, otherwise we're in trouble. How are we feeling? Bad, is that what I heard?
Not bad.
Oh, not bad. Didn't hear the word not. She says not bad. You guys want to try B on your own?
Yes.
Yes? I got one yes. Okay, you just vote for all of you. Try letter B on your own. I was going to make you do it anyhow. Letter B has an even number of tangents and an even number of secants. So what are you going to do?
Use the first thing.
Yeah, use this first one, right? Pull off a secant squared. Let u be tangent. Let's see what happens. I'll write it up here. You guys work on it for a little bit. We'll see how far we get. Shorter than that last one, or it should be. So the first thing I want to do is rewrite this secant to the fourth as secant squared times secant squared. I talked about 2 or 3 or maybe 4 of you who wanted to write this as secant squared squared, which isn't wrong, but it actually helps to write it this way. It's what we just talked about, Brielle, because this part right here, we recognize. That's the whole reason we pulled one up. We need to recognize that as the derivative of tangent. If you write it as secant squared squared, it's not really clear what's going away and what's left, and you can't square your du's. So everyone agree that's the derivative of tangent right there? So then, we let u equal tangent x. They're not getting noticed. So let u equal tangent x. du is secant squared x dx. So this part right here is my du. Done, right? What's this?
U to the 6th.
U to the 6th, but we chose u to be tangent, right? That's just u to the 6th. So then I'm just left with this little guy right here.
1 plus dash squared.
Right, then we have the identity, which is on the top of your page, or it's over here. Secant squared is equal to 1 plus tangent squared. So if this is 1 plus tangent squared, and u is tangent, that's 1 plus u squared. 1 plus tangent squared. You see it? So some of you wanted to square this, but one of your secants is already gone from over here. And you only had one more secant, one of your secants squared, excuse me. Your other secant squared is over here. So then we have the integral of u to the 6th times 1 plus u squared du. We distribute. We integrate. And then we put our u's back in there. So it's all like a giant puzzle. It's about looking for derivatives that you know hanging around in there, So I was looking for a secant squared in there, because I know that's, and making sure I'm left with evens after I pull off the derivative I know and make sure everything else is even. The reason everything else has to be even is to use our identities. And then we can plug everything in, life works out pretty, yes.
Could there be other ways to solve this, or would you eventually end up solving it that way?
That's a good question. So her question was if there are other ways to solve this. And there's actually multiple ways. A lot of times, especially when I get stuck, or maybe I don't have case 1 or case 2, like, well, where's case 3? What else? It's not working out. A lot of times I use this identity, that tangent equals sine over cosine. And I use the fact that secant is 1 over the cosine. I quite often will just change everything to sines and cosines and work it out that way. And my answer might have all sines and cosines in it, but it's still equivalent. So a lot of times you'll get an answer that looks completely different, but it's still the same thing. A lot of that is true with the odd powers of, like if you have odd sines and odd cosines, depending on which way you choose, which one you peel off, your answer will have all cosines, mine will have all sines, but they're equivalent because of the identity. I got another question, I thought? Yes.
So what if we have secant to the 6th power? Do you have to do 1 plus u squared twice?
Oh, if it was secant to the 6th, yes. So everyone hear his question? His question was, I'm gonna write on top of it in green. He says, what if this was a 6 right here? If that was a 6. Once I pulled off these 2, I would have been left with 4 right here. Right, secant to the 4th, which is secant squared squared. So I would have had to do another one right there. Because this part was the secant squared, and I'd have to square it. Is that what you're asking? Totally changed the problem with that green, but that's the whole idea, is you should be able to break everything down into secant squareds or tangent squareds based on what you're working with. And go from there. It's a giant puzzle. Just tell yourself you like puzzles. I like puzzles. It's very satisfying when it works out. When it doesn't work out, it's frustrating. So let's talk about when it doesn't work out. What about when it doesn't work out? Like, for example, what is my next example? Where is it? Here's my next example. Just the regular old integral of tangent. Example C. And like, it looks so easy. There's nothing there. It's just one little function. I don't know the integral of tangent off the top of my head. Actually, I do, but pretend I don't. Most of you don't know it. Most of you don't know it, but you actually know enough to figure it out. So all I see is tangents, and I'm like, okay, do I have an even number of secants? No. Maybe there's 0 of them. So, do I have an odd number of tangents? Well, yeah, but I don't have anything else to do this. I can't pull off a secant tangent, there's nothing there. So I'm starting to panic, like it doesn't fall into any of my categories. So when I start to panic, I revert back to just change everything into sines and cosines. So I'm just going to rewrite the problem as sine x over cosine x. Makes me feel a little bit better. Looks more familiar. And then, my first thought for anything is, can I do a u sub here? Will a u sub help me in any way? He says cosine. If I let u equal cosine, what would du be? Sine. Hey, look at that. It's hanging around. If I let u equal cosine, the derivative is hanging around up here. Let's try it. U equals cosine x. I agree the derivative has a negative in it, but I'm not so worried about that. We can deal with negatives a lot better than functions that aren't supposed to be there. Negative sine x dx. So that means I have negative 1 over u du, because this part right here is negative du. All of that is negative du. Yeah? 1 over u, negative du.
It just would be a natural log.
It is just going to be a natural log. Right? 1 over u, we know how to integrate that. negative natural log of u. Make sure you put your absolute values on there when you integrate. We have to force it to be positive or it's undefined. So the integral of 1 over u is negative natural log of u plus c. Negative ln of cosine x plus c. Now this is technically correct. Somebody do exactly what I've asked you not to do and take your phone out during class and Google the integral of tangent x. I bet you this is not the answer. Go ahead, anybody dare take your phone out in class after I asked you not to? Please do it now. The integral of tangent x, what's Google tell you it is? Or Wolfram Alpha or whoever, whatever website you use. You guys have lots of them, I know. I can always tell if people use them on their homework too. Like, oh, that's an interesting technique. It works. We haven't talked about that. Anybody Google integral of tangent? This is not the
Natural
most.
log of secant.
Aha! This is the most common one.
But I mean, there's another one that shows, there's two for this one that I pulled up. It says the one that we have up there is right, and there's also the natural log of secant x.
Mm-hmm.
But so we have both those.
Yours, so wherever you Googled showed you both?
Yeah.
How can they both be right?
You can do 1 over cosine.
Aha! You know your powers of, your properties of logs. Here's a negative in the front right here. That means I could move it up here and put it up there. Remember those properties of logs? I have to erase it if I move it. So if I'm working with what I had, that's the natural log of cosine x to the negative 1. But a negative 1 exponent is the reciprocal. What's the reciprocal of cosine? Secant. Right? 1 over cosine is 1 over cosine is equal to secant.
So in that case, would you accept either one?
Yep.
And would Webesign accept either one?
Yes.
No.
WebAssign's pretty smart that way. It knows all those identities. It accepts lots of different ways. But they're identical. And so here's another example where let's say I gave you this problem on the lab, which I have to remember to give you the answers. And my answer might look like this. But you did the problem and you came up with this. Do not assume you're wrong. First check and use some algebra and some trig to see if maybe they're equivalent to each other. It may not look the same as mine. It all depends on which way we started the problem. Natural log of the secant. Who would have thought? When these fail, I always change the sines and cosines. I'm like, okay, I can make this work if I do that. Like, somehow I think better that way. Okay, so the last one I want to show you is the integral of secant x. It's not even on your page there. The last one's actually just, letter D is just evaluating one, so it's not much different. But the integral of secant is going to come up all semester long. And so we're going to do it now and put on the bottom of that page, is that 30? Yeah, page 30. And then we're going to put a nice little box and stars and hearts around it so you can find it later, because you're going to need it for reference. And to do it involves a trick that I will not expect you to memorize, but I'm going to show it to you once. So add that to the bottom of your page, somewhere. Our last one, I swear. So if I asked you to do this on a test, and you didn't know the algebra trick required, what do you think you might try?
1 over cosine.
Yeah, maybe 1 over cosine. We like cosines better anyhow, so maybe we'd try this. But then we can't do a u sub because the du would have to have a sign in it, which we don't have. So we'd still be kind of stuck even after we rewrote it. So that doesn't help us. And after that, we're out of ideas. So here's the trick. What we do is we take that secant x and we multiply it by 1. A fraction, a very messy fraction that's equal to 1. And it is secant x plus tangent x over itself. And the question is, no, I don't think I would have come up with that either. I only know the trick because I've seen it for years. We agree that's identical, we've just changed it by multiplying by a really messy version of 1. Which is why I'm never going to expect you to do it on your own. How do you memorize that trick? I don't know.
That's the truth.
So then I'm going to simplify that, and the top will be secant squared x plus secant x tangent x. Right? We're combining all that. Distributing over secant x plus tangent x. Yes. Just multiplied out the numerator. You guys good? Let u be that denominator. U is secant x plus tangent x. What's du? Derivative of secant is, I see you guys looking over my shoulder there. Secant x tangent x plus derivative of tangent, secant squared.
Also the D cancels out from the top.
Yeah, that du is that entire numerator. You guys see that? My entire numerator with that dx is my du. So I'm back to what I just had over there. 1 over u du. I still don't know who came up with this, who figured it out someday, but they had to be playing around for hours to figure that out. It's pretty cool, but I don't know how they got there. My brain wouldn't have worked that way for a long time. So the integral of that is the natural log of u in absolute values plus c. So the integral of secant x is equal to the natural log of secant x plus tangent x plus c. And if you Google that one, I think that's probably the only answer you'll find. Maybe there's another one, but that's the one I see 99.9% of the time. Make sure you put a box or something around this, or stars or arrows or whatever, because every once in a while when you're working on lab assignments through the next few weeks, the integral of secant x will show up every now and then. And when it does, you don't have to do the work every time. You can just copy that down. So if you end up with a problem though where you have to integrate secant x, I just want you to copy that part down.
Would you give this to us on an exam or should we have it?
I'd probably give it to you if you need it on exam. I'd give it to you. I try to just kind of avoid it on exams so that I don't have to remember to put it on there. Yes.
Wait, are you gonna give us secant squared x or secant root of x?
Well, the integral of secant squared is just tangent, right? Right. So once you have the other powers, our other rules kind of come into play. Yeah. So that's actually another point. On the lab assignments, some of you I wrote, how'd you get here? Where's your work? You want to make sure you're showing me your integration because that's the whole point, that you show me you know how to integrate. Don't tell me what the answer is. A lot of you were setting them up and writing the answer with no work in between. The whole point is I know you know how to do it. We know the calculator can do it. Somebody programmed it. But someday you might have to program a calculator. So we need to make sure you can do it. Okay, so that last one, the letter D, is similar to what we did earlier. You just plug in the bounds. That's not much different. You can try that one if you want. We can check our answers. We have, what, 9 more minutes? When I see you on Tuesday, both 7.1, integration by parts, and 7.2, trig integrals, are both due on Tuesday.
What about 6.5?
And 6.5, thank you. We already did 6.5. 3 sections due on Tuesday. I have the answers to the Chapter 7 lab assignments that I'm going to pass out right now. Questions? If you want to hang around and work on that last one and check your answers, you can do that. If not, I'm going to lab in